Next topic is galactose and fructose metabolism. Now, this metabolism is very easy because we're going to focus on a couple of major inborn errors for this. Now recall, where do we get galactose and fructose from? We get it in our diet. So galactose, where does that come from?
Milk.
Comes from milk. More specifically, lactose. So lactose is a disaccharide of glucose plus galactose. And where do we get fructose from?
Sucrose.
Yeah, sucrose. Sucrose. That's glucose plus fructose. Where else do we get fructose from?
Subsidized corn.
Says what?
Subsidized corn.
Yes, absolutely. It's called high fructose corn syrup. It's really good. If you've got a stock portfolio and you're investing in places, that use this stuff, you can buy barrels, 55-gallon barrels, and pour it into food. So why do we like fructose over glucose? Taste, yeah. Fructose tastes sweeter. And we are now addicted to that sweet taste. Gotta have it. Okay, so we've looked at the metabolism of glucose, and now let's turn our attention to fructose and galactose. So let's start out with fructose. So fructose, we know, comes into the intestine by GLUT5. Is that active transport?
No, facilitated diffusion.
Yeah, this is facilitated diffusion. So the only movement of fructose in the body is going to occur exclusively through GLUT5, and there are no other transporters in the body. So there is no GLUT1 through 4 versus SGLT1 and all that, because fructose is not the most important carbohydrate in our diet. Glucose is. So now, as physicians, you have to be very proactive in the community to reduce the obesity problem. And one of the ideas is to reduce fructose consumption. Why is that so important to reduce fructose consumption, to reduce the obesity problem, when you consider GLUT5 in the equation?
Because it's uptake is concentration gradient.
Yeah, good. Uptake of glucose is concentration dependent. So glucose uptake is critical because glucose goes in the oral cavity, comes out, can possibly come out the anal cavity, and you've got a continuum. So as it's moving through, you got to pull that glucose out as rapidly as you can. Fructose, not so much. So if you reduce your fructose load in your diet, you reduce this concentration dependent effect. Fighting glucose uptake, I wouldn't even bother wasting time with that because that SGLT1 is so powerful with that secondary active transport. But reducing fructose, reducing your concentration, that means less getting into the body. So the primary site for fructose metabolism is going to be the liver. Now what the liver is going to do is it's going to take this into the cytoplasm by the GLUT5 transporter, and we are going to use an enzyme called fructokinase. So the liver has glucokinase for GLUT2 for glucose modification. Here we're going to have fructokinase. And we are going to generate fructose 1-phosphate. It was a good try, though. Let's try to keep this as consistent as possible. Nope, I'm going to throw a monkey wrench in for you. So fructose 1-phosphate Now, because it's a carbohydrate, we're not going to create an entire new energy production scheme. What we want to do is take this molecule and put it into glycolysis, okay? So what we're going to do is we're going to take this, we are going to cleave it with aldolase B, and we are going to generate glyceraldehyde plus DHAP. Now DHAP, remember, is dihydroxyacetone phosphate. This is the same substrate that we generate for glycolysis for oxidation of glucose. So this is going to be converted into glyceraldehyde 3-phosphate. Because the fructose 1-phosphate doesn't have the bisphosphate like fructose 1,6, the product, instead of glyceraldehyde 3-phosphate, is going to be glyceraldehyde. So this will be phosphorylated by an enzyme called triose kinase. So now what we've done is we've taken our fructose and we've modified it so that now we can enter the glycolytic cycle. And then, of course, this can go on to generate ATP. So this is where fructose is a rich energy source for ATP. Now, here's the metabolic problem with glucose, with fructose. Going through this pathway, what we need to do is get down to glyceraldehyde 3-phosphate. This is past the juncture of PFK1. Remember Dr. Alcorn mentioned about the problem with fructose and fat development? And I mentioned I'll take you through that. Well, this PFK1 is supposed to be converting fructose 6-phosphate to fructose 1,6 bisphosphate. And then this gets cleaved into DHAP and glyceraldehyde phosphate.
Glucose,
Now,
right?
yes, this is the glucose pathway here. What we're going to see tomorrow is that we also need to do this reaction. So once our glucose has been oxidized sufficiently so that we generate a lot of energy, remember I said the next step is to store glucose. And so our energy charge is going to be detected by ATP. And the ATP is going to slow the activity of PFK1, which is going to slow this conversion. What that allows us to do is now store glucose as glycogen. Because we're slowing this substrate of PFK1 builds its concentration, and now these reactions reverse so that we can make glycogen. Okay? Now, in the liver has the capacity to make fat. So when our glycogen stores are filled, and we are still oxidizing glucose, we are going to be pushing the glucose down through this pathway, and then once we get to the TCA cycle, if our energy charge is really high, which it is, we can now shuttle that material into fatty acid synthesis. So that's normally what happens with glucose. First step of oxidation is generate energy for ATP, get your ATP levels up. Then when that levels up, you want to slow glycolysis to fill your glycogen stores with glycogenesis. And then after that's done, you can take the extra glucose, turn it into fats so you have long-term caloric storage. Now where does fructose come into this? Look at where it's entering glycolysis. It's entering below PFK1. If fructose metabolites entered above, prior to PFK1, the fructose could be used to store glycogen. But it's not. So when the energy level goes high, the fructose is funneling into fatty acid synthesis. And so the fructose can be used for energy, but once your energy levels are high, you've got no place to go with the fructose except into fatty acid synthesis. So high fructose corn syrup, which has glucose in it, add that extra load of glucose, extra load of fructose, and now you're feeding into fatty acid synthesis by two independent pathways. And this is what's causing the major obesity problem that we have because of that fructose supplementation in our diet. Now let's talk about two different diseases: hereditary fructose intolerance and fructosemia. So there's two specific inborn mutations in this fructose metabolism pathway that can occur. One is at the level of fructokinase. The other one is aldolase B. So if we have a mutation in fructokinase, what that's going to prevent is the liver from taking fructose and converting that into fructose 1-phosphate. So if we have a mutation in that particular enzyme, what is that patient going to experience? Fructosemia. Because this GLUT5 is reversible. Remember, that's facilitated diffusion. So as the concentration of fructose builds, it's going to move to its lower concentration. So the fructose comes in, increases its concentration because it cannot be converted into fructose 1-phosphate. So now the fructose exits GLUT5, leading to fructosemia. It's the GI block, so it's always diarrhea, right? Diarrhea or vomiting. So these symptoms of this particular inborn error are clinically very mild. Because as your fructose levels build in your blood, what do your kidneys do? You excrete it. And it's mild because we have a path to get rid of the fructose. We have an escape route. What about a mutation in aldolase B? What will result from that mutation?
Buildup of fructose 1-phosphate.
Yeah, you're going to have an increase in fructose 1-phosphate. Now, what would the symptoms be on this individual that has this mutation? Are they going to be mild or severe?
Severe.
Severe. This is hereditary fructose intolerance. And it's severe for two reasons. The first thing is that fructose 1-phosphate is what's considered an osmolyte, which means that it is water active. It's going to be binding water. So water is going to flow into cells as the fructose 1-phosphate concentration begins to build. So that can cause hepatocyte damage. The other problem is that people with aldolase B mutations, their fructokinase is operating just dandy. And so if they're taking fructose in their diet, it's going to be transported by GLUT5 activity dependent on the concentration. Fructose comes in, fructokinase phosphorylates into fructose 1-phosphate, and now we get stuck. So that's what's building our concentration, but this reaction is also continuing. In order to phosphorylate fructose, we're going to be using ATP. Now the problem with this is our reverse reaction by our ATP synthase complex. This is what our ATP synthase complex is doing. It's taking ADP plus inorganic phosphate. It's putting in the energy because of the spinning head to make ATP. Now, if we block this at fructose 1-phosphate, we're going to have plenty of ADP. But what are we going to be missing? The phosphate. And so the problem with aldolase B is that we are trapping all of our inorganic phosphate in the form of fructose 1-phosphate. And we cannot process this substrate without aldolase B. So we are significantly depleting our phosphate, and so our production of ATP is going to be hampered. And it's for this reason why aldolase B is a horribly, horrifically difficult patient management. Or is it?
Don't eat fructose.
Don't eat fructose. So these type of inborn errors of these carbohydrate metabolisms are very easy to take care of. You just eliminate fructose from the diet.
Piece of cake.
You just read my mind. I was just going to say, now how easy is that? Yes?
Does the aldolase B deficiency affect substrate level and oxidative phosphorylation as well, or just
That's actually this aldolase B, this isoform of aldolase is relatively specific for fructose, 1-phosphate, and then aldolase A, which is also in muscle and liver, that will take care of fructose 1,6. So that direction is okay. So getting rid of fructose, you can imagine your patients, if you tell them this, fortunately it's a rare disease, but if you tell them you got to eliminate fructose from your diet, well, how do I do that? You read everything and you study everything that you eat. So what's the most obvious thing to get rid of? Dairy, right? Eliminate the lactose. Oh, excuse me. No, I got ahead of myself. Fruits, yes. Reducing your sucrose consumption. Reducing your sugar consumption. How hard is that?
It's super easy.
It's super easy. Yeah. Oh my God, without my sweets, I can't survive. Fortunately, I am not hereditary fructose intolerant. Okay, so again, these symptoms here, these individuals is vomiting, diarrhea, everything that you've heard of that is relatively non-specific. Okay, we good on that one? Questions? Now, is there something on there? Okay. So let's move to galactose. Galactose is a little bit more complicated, which makes it a little bit more interesting. So again, the liver is going to be the primary source of metabolizing lactose. And that means that we have to take the galactose inside the liver cell. So what transporter is going to take galactose inside the liver cell? Wow, that was quite a variety. This is where distributions on clicker questions are awesome. I've heard GLUT something, and then I've heard SGLT1. What does the liver use to take glucose in? The liver. One of the glutes. Oh, you're right. Okay. How does galactose get into the intestinal enterocytes from the lumen? Yeah, why? I thought that was a glucose transporter. It's an epimer, yeah. So glucose and galactose almost look the same. So translate that knowledge to the liver, and what's internalizing galactose into the, what's taking in galactose inside the liver? One of the glutes. I'm going to write up a special question for somebody here. If glucose looks like galactose, GLUT2, right. Not GLUT4. GLUT4 is on muscle and adipose only, and it's insulin responsive. So GLUT2 is on the liver to take up glucose and galactose. So we are going to use GLUT2. So it's concentration dependent. And then the first step is by an enzyme called galactokinase. And we are making galactose 1-phosphate. So it's the same reaction we've seen before. Now this is where it gets a little sketchy. We have to convert the galactose 1-phosphate into glucose 1-phosphate. The reason we have to do this is because we don't have a separate oxidative pathway for galactose, just like we don't have one for fructose. We need to get it into the glycolytic pathway. And so to do that, we need to convert it into a glycolytic substrate. So now to do this, we are going to use a compound called UDP glucose. And I'll explain in a minute why we have to take this little bypass. So all we're simply doing is taking the galactose 1-phosphate and we are exchanging that with UDP glucose to generate glucose 1-phosphate, resulting in UDP galactose. So essentially what we're doing is we're taking the sugar portion, galactose, and switching it for glucose by using this UDP conjugated molecule. Whenever we're forming and modifying sugars, where we're switching sugars around or adding sugars together, we're going to be using it in the form of a uridine diphosphate. So that's a nucleotide. Now the enzyme that does this is called galactose 1-phosphate uridylyl transferase. Uridylyl. Uridylyl. Okay. You'll never forget this enzyme. And that's good because that's one of the inborn error points. So now, once we do this transformation, we're going to take the glucose 1-phosphate and we're going to convert this into glucose 6-phosphate. Using an enzyme called phosphoglucomutase. All this is moving the phosphate from the number 1 carbon to number 6. This same enzyme we're going to see in glycogen metabolism. So we're taking advantage of another enzyme. And then once we have glucose 6-phosphate, then we can go into glycolysis. Or we can go into glycogen synthesis. So galactose can contribute both to energy production and glycogen carbohydrate storage. Now, why do we do this funny little side reaction here? Well, the problem is that This enzyme right here is very, very reversible. And we use this direction here on phosphoglucomutase when we're synthesizing glycogen. This direction is glycogen degradation. Now, if we're I used to do this seamlessly when I was younger. If we're synthesizing glycogen by taking advantage of the reversibility of this particular enzyme, this molecule here is what actually is going to glycogen synthesis. If we could possibly go in this direction, we would be depriving ourselves of synthesizing glycogen. So this enzyme is not reversible. What you would think is because galactose and glucose are epimers of each other. So all you would need would be a pyramase. It's a single enzyme. All you have to do is flip the hydroxyl group. But we don't have that enzyme because we cannot deplete this substrate from glycogen synthesis. We have to make sure it goes there and not this way. So in order to do that, we do this fancy little side reaction. Now in order to regenerate this, this is where the aperamase comes in. Is now we can convert it to here to continue this reaction. So, painful a little bit, but that gets us to galactosemia. Now, there's 3 forms of galactosemia. There's a milder form, just like fructosemia. That is a mutation in the galactokinase enzyme. That is the mild form. It's mild for the same reasons as fructokinase mutation. Is that if you block the formation of galactose 1-phosphate, galactose has the opportunity to reverse and go back out into the blood and be excreted by the kidneys. The classical one, and it's actually called classical galactosemia, is a mutation on the transferase enzyme. So a mutation here is going to lead to a severe phenotype. Because the galactokinase enzyme is still active, this is an ATP requiring step. And you have the same types of problems with fructose 1-phosphate. You've got dysosmoregulation and you've got trapping of the phosphate. Now there's another kind that is extremely rare, and that's in this enzyme here. I looked it up because up until I was redoing this presentation for this block, I had no idea there was a mutation in this enzyme. And then I looked it up, and I think there have been 8 cases ever recorded on that enzyme. So, you know, it's like, don't pay any attention to it, but just kind of be aware. The type of questions that you'll see on first aid, step 1, all that kind of stuff, are focused on these 2 points, the galactokinase and the uridyl transferase. And those are the ones that lead to the galactosemia that is most common, which is still very rare. Now, different than fructose, high galactose concentrations, high concentrations of galactose, as well as galactose 1-phosphate, has a feature causing cataracts. So this is one of the first physical symptoms of, and now we're talking, these are inborn errors, so these are genetic errors, so these are going to be diagnosed like in, 6-month-old, 1-year-olds. They will start developing cataracts with both of these mild and severe galactosemias. Now, how does that come about? Well, the galactose itself or the galactose 1-phosphate can be processed by an enzyme called aldose reductase. This enzyme, we're going to see this one in diabetic complications, but what this does is it takes the aldose form, the aldehyde form of the sugar, and converts it into the alcohol form. So it makes galactitol. So all we're doing is taking the aldehyde group here and performing a redox reaction by reducing it, creating the alcohol version. This cannot leave the cell by GLUT2 because it's not galactose anymore. Galactose is a ring structure, 6-membered ring. This is open. Now what this is going to do is it's osmotically active. So there's an enormous amount of water that this can bind. So on our lens cells, which are very delicate, this reaction is going to occur, and it's going to be galactose concentration dependent, making more of this alcohol version, putting more water and increasing the osmotic pressure inside the lens. And that is going to cause the proteins to precipitate and form the cataract. So that is a classical presentation with galactosemia, is that cataracts. Now, how do you treat this disease? Don't give them galactose. Yeah, take galactose out of the diet. Because if you take galactose out of the diet, you prevent all of these reactions, and you don't build up that product, that substrate intermediate. Are you depriving the individual of caloric needs? Nope, because glucose processing is just fine. Fatty acid oxidation is just fine. It's just going through these two, bypassing these two mutations. Okay, yes?
What is it called when there's a deficiency of epimerase?
That's type 3. So this is type 1. No, I'm sorry. This is type 2. So the galactokinase is type 2. The transferase is type 1, which is also called classical galactosemia. And then the paramase is the type 3.
And can both glucose 1 and glucose 6-phosphate enter into glycogen synthesis?
Yes. Yes, the galactose phosphate, that can be converted in, as long as you can convert it down here, as long as you don't have this block, then you can get it down to where you have a substrate for glycogen synthesis. Right. Yes?
But glucose 6-phosphate has to go backwards to glucose 1-phosphate to go to glycogen, right?
Yes, because for glycogen synthesis, we're going to look at glycogen synthesis, I think, tomorrow, and we have to add energy into doing that. So we're going to go through from glucose 6 to glucose 1, and then we're going to make UDP glucose, and then we're going to start linking them together on there. But the entrance point really is glucose 1-phosphate.
So that arrow just shouldn't be there. Like glucose 6-phosphate, right arrow, glycogen.
This is glycogen degradation.
Move your finger down just a tiny bit, and then a little bit to the right. Yeah.
Yeah.
Oh, yes. Wow. Yeah, that's missing a step.
Okay.
Thank you.